Hello, I'm Dominik Scheder from Shanghai Jiaotong University. I will tell you why PPSZ is better than you think. And because this is a very cryptic title, let me expand it. The KSAT algorithm PPSZ is better than the previously known bound, and the improvement is quite small and also shrinks as K grows. All right, my talk will have 4 parts. Part 1, what is KSAT? What is SAT? You see here a formula in propositional logic. Here you see a truth assignment that makes the formula evaluate to false. Here you see an assignment that makes the formula evaluate to true. So this is called a satisfying assignment. And this is SAT. It's the decision problem given a formula in conjunctive normal form. Decide whether there is a satisfying assignment. So what is KSAT? Well, K refers to the maximum clause width. In this case, it's obviously 4. So KSAT is the same as SAT restricted to KC in the formulas. Part 2, the PPSZ algorithm. Actually, part 2a, the PPZ algorithm. So this is a SAT algorithm. It's best viewed as an algorithm between encoder and decoder. So we have an encoder that wants to encode a given satisfying assignment with fewer than n bits, such that a decoder can recover it. The point is, when you have this setting, you can imagine that this connection is capped, and even without knowing the encoding, the satisfying assignment, the decoder gets fed random bits. And with that probability, the encoding actually occurs as a prefix, and it still successfully decodes the assignment. There is an additional input, a permutation of the variable. So this is going to be very important. So we should write encoding alpha pi, and it's going to be a random encoding. So we should put the expectation around it. We can apply Jensen's inequality. So we can focus now actually on the average code length of this assignment. So 2 things: how does the encoder work? How does one analyze the average code length? This is how the encoder works. I will show you at an example. So I write my clauses as these little blocks. I find it a little bit neater. My satisfying assignment is the all one assignment. This is my permutation. And the encoding works like this. I just output bit after bit, unless the previously set bits make the next bit obvious. So here you see y is the only survivor in its clause, so it must be set to 1. So we can skip this because the decoder sees y is obviously 1. So in the encoding, we save 1 bit. Now let's play the whole game again with a different permutation. Again, we can skip y because it's the only survivor. And now we can also skip x. So in this permutation, we can skip 2 variables. And the lesson we have learned, all permutations are equally likely, but some are better than others. Okay, keep this in mind for later, because this is where our improvement sets in. Okay, so here's the pseudocode. I introduce some notation. So when we can infer a variable, I write I x equals 1. And now let's analyze the average code length. Throughout the talk, I will assume that 111 is the unique satisfying assignment. Right, so it's easy to see there must be a clause of this form, x, y bar, z bar. And if x occurs last, it's going to be the last survivor, and you can infer it. And therefore, this expectation is at least 1 over k, and your success probability gets boosted by this n over k term in the exponent. So this is the paper by Paturi, Kudlak, and Zain from 97. Yeah, okay. So now let's put Michael Sachs back into the picture. And the change to the algorithm is minimal. Instead of looking at single clauses, we look at W tuples of clauses. So I think it's again best to see this at an example. It's again the same example as before. We can save y. But now look, we can also save x in this case, because when we look at these two clauses, they together imply x equals 1. So we can skip it because w is 2. We look at pairs of clauses. So you see here, if you make w larger, you can skip more variables. The encoding will be shorter and the success probability will be larger. So how large should we choose w? Well, not too large, because then it gets very expensive to iterate over all w tuples. But actually, it turns out it doesn't matter. So for example, w, you can choose it to be log n, you can choose it to be log n. For everything that comes now, it doesn't matter. It should be like a slowly growing function in n. Yeah, this was a PPSZ. So now let me show you the previously known bound. To analyze PPSZ, I like to think of it as a game between a prover and a denialist. So denialist says, well, I can't just as well set x to 0. The prover says, no, you're going to violate this clause. Right? But I can set y to 0. No, you're going to violate this clause. I can set t to 0. No, you're going to violate this clause. And of course, the prover can always find a clause because by assumption, the all-wine assignment is the unique solution. But the prover runs out of patience. And at level 3, the prover says, let's not go further. OK, let's keep it at level 3. And the denialist can say, okay, whatever you say, but I can also set u to 0. And by arguing back and forth, they build up this tree here. This tree is called the critical clause tree, and it's absolutely central in the analysis of PPSZ, and also the improvement by Hansen et al., and also the improvement of this paper. So this is basically the central object that you see here. And why does it make sense? Because imagine you have this permutation. What happens when you encode x? You already have set r, s, u, and c to 1 because they appeared earlier. So this already kills the red marked literals. And now you see all escape paths for the denialist are blocked. So now the denialist loses this game, and we can infer x equals 1. So in general, we built this tree up to height, let's say log w. So we have fewer than w clauses. And the moral is here, if all escape paths are blocked, ix equals 1. So this motivates the definition of a cut. A cut is the set of all permutations where the red, the red squares block all escape paths from root to bottom. And the lemma here is if cut happens, then you can infer x. Yeah, that's it. So we have to find out the probability of a cut. If a tree has height 1, it's easy, right? Then the cut happens if I appears last. So this is 1/3. For this, it's more difficult, but with a computer, we can calculate it. So it's 31/70. And if we go deeper and deeper, it grows. Okay, so this is all very fun. It turns out in the limit, if you make this tree infinite, it's easy. It's actually easier if you look at an infinite tree. So let's call this probability S3. So what is cut in an infinite tree? Well, if you're an infinite tree, then basically what it is, so the red part is whatever comes before X. The green part is whatever, basically the component containing the root. So whatever is reachable, the escape paths. And if the green part is finite, then cut happens for this infinite tree. Good, so why do I say S3? Because of 3-sat. And in general, I would say SK, but then you don't have a binary tree. You have a k-1 array tree. You have a different formula, but conceptually, it's the same. Okay? And also now, when you talk about infinitely many things, we cannot really talk about permutations anymore. We cannot really talk about random permutations. We talk about random placements. So every node gets a uniform random number in the unit interval. So that's basically equivalent to permutations in the finite case. So here's the summary. You relate the success probability to the average code length. You relate the code length to the cuts, and you argue that the cuts somehow behave as in the infinite tree, and you get the theorem that says, well, your success probability is boosted by this extinction probability sk. Okay. That was part 3. Now it's halftime, second half of the talk. How can you make this better? So this paper is actually not the first improvement. There has, 2 years ago, been a paper by Hansen, Kaplan, Samir, and Zwick. Without going into details, let me just show you where they change things. They say, well, we actually can do better than feeding uniform bits. And then they don't get a 2 here, but 1.99. This improvement that I'm showing you is different. I show you how you can stick in better random permutations, and you obtain a smaller average code length. So we have to prove the following lemma, inspired by the sentence that I showed you before. All permutations are equally likely, but some permutations are better. So actually, we can define a distribution Q under which the code length is smaller. But there is a catch. The definition of Q uses knowledge of the assignment alpha. So what you do, we leave PPSZ unchanged and we imagine that it samples pi according to Q. So what does it mean? This is actually, this imagining step is mathematically very simple. So we write the success probability, this expectation, we write it as a sum, and we force this Q into it. We apply Jensen, and we now basically get expected code length under Q, but we get a penalty term, which is the Kullback-Leitler divergence. If you're careful enough, without going into technical details, you can make the improvement linear in epsilon and the Kullback-Leitler divergence quadratic in epsilon. So that's the whole point. So if you now are careful enough and choose epsilon small enough, this gives you a linear improvement. And in the exponent, it will then give you an exponential improvement. Good. So we have to prove this lemma, and I give you a proof by by picture and example. So there is an easy case. Imagine you have these 2 variables, x and u, and this is your permutation. Now you can easily see cut of x happens, but for tu it doesn't happen. Now when you move x to the left, this changes, right? So now z comes afterwards, and now tx stops to have a cut. So the event cut now goes from happening to non-happening. If you further decrease x, then cut of tu suddenly starts happening. So it's kind of obvious that cut of tx is increasing in pi x, and everything else is decreasing in pi x. So that means if we ask the question, should we decrease pi of x, should we move x to the beginning of the permutation, then tx says no, 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 and everybody else says yes, yes, yes. And now, if there are many trees that says yes, 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 it's better. It pays to move pi of x to the front. So now you have 2 cases. Either you have many variables of large degree, and then you can define Q to move these variables to the front, or there isn't, and then it's easy to show the following. You can find linearly many sibling pairs. So what is a sibling pair? A sibling pair is this. It's basically the 2 children in a critical clause tree, the 2 children of the root. So now here you see 3 pairs. The first 2 of them are disjoint, and the third one overlaps with the second. So like this, the first 2 are disjoint. Why is this good? Because now we define Q to make Y and Z positively correlated in some way. So we define Q such that it is still uniform on every variable, but pi of Y and pi of Z are positively correlated. And I would argue that this is better for cut of Tx, and for every other tree, it's at least not worse. Well, except if special case A, B, C, or D happens, and these are the main technical challenges. But if you can deal with these technical challenges, then you can prove the lemma and you can improve whatever your formula is. Yeah, so for 2 more minutes, let's peek into these technical difficulties. We have already seen the cut depends monotonically on each of these events, right? So these events happening can only be good for the cut. But if you look closer, if you look at these 2 events here, so here we have 2 events where the positive correlation is good because cut of Tx depends andly on these 2 variables. Down here, if you have an ancestor-descendant pair, it depends orly. And I let you figure out how to formally define andly and orly. And if it depends orly, then the positive correlation is bad. So the thing is, what if you have the sibling pair where the positive correlation is good, but in an ancestor-dependent pair in a different tree, it's bad. So now you have to argue. You have to argue, well, what are the kids of Y in the top tree? And usually they should be the same as in the bottom tree. So, okay, usually, right. And if that happens, you see in the top tree, Z appears twice. And this alone boosts the cut probability. So now you have to quantify things. You have to, how much does it boost? And how much does this ancestor-descendant pair at the bottom, how much does it harm the bottom tree? So from here on, it's basically a bunch of meat in the middle arguments. And at the end of the day, you will see whatever your formula is, you can find a permutation. No, you can find a distribution of permutations that is linearly better. So here's the summary. You define this permutation depending on the formula. And then you don't change the algorithm, but you simply pretend that this is your distribution. And you have to pay a small price, which is the Kullback-Leibler divergence from Q to U. And that's it. Then you have exponentially better success probability. Thank you.